Hi, I'm about to have my home gas hot water system replaced with a heat pump system. I've done several videos on this. The whole idea is that we can use excess solar power, and basically this is the only gas thing that we've got. Well, this is the only non-electric thing that we've got left, of course. We've got the 8 kilowatt, nominal 8 kilowatt system spread over two different solar panel systems on the roof. One N-phase micro inverter system, one Sunny Boy system, and yeah, but like everything is electric. We've got the electric car, which we charge using the Zappy controller, so it's practically 100% powered from our excess solar energy, so effectively got a solar powered car, and everything else in the house is solar power. The only thing that we've got left that's gas is the hot water. We do have an outdoor barbecue, but we're going to change that over to bottle because we rarely use that, so our bottle will be fine. But yeah, so instead of going with like solar hot water system, which will just take up roof space and that'll only be used for the hot water anyway, yeah, we'll go for a heat pump hot water system, and we'll see what the energy requirements are. Anyway, it's being installed tomorrow. So what I've got here is a Rheem high efficiency 170 litre outdoor jobby. It's the 88 series. Not sure if you can see that. It's really old. It's the original one that came with the house. The house is mid 80s, something like that. So yeah, it's still going. It still actually works. We've had no issues with it whatsoever. So obviously we've got gas inlet down here. This is the cold water in, and then up here we've got the hot water out. And over here we have a relief valve. So I want to check the temperatures, and then down here I've taken the panel off. You can see that there's the gas valve, and then the pilot flame is under there, and we'll have a look at that. It's never gone off, like, well, no, maybe once, I think. Maybe once it went off in the 18 years that we've been here. So anyway, I don't know. It's got no temperature on here, so it's hot. I did actually measure the temperature with the thermocouple the other day, and I was getting 53 degrees out of the pilot. Outlet temperature here, my thermocouple's saying 51. Right, I'm in the furthest most point in the house where we can get hot water, and ouchie, that is hot. This is in the laundry, and no, I don't think we have insulation on the pipes either in the roof. It doesn't seem to be a big deal here. I measured just the other day inside, yeah, 51. It's on par or only a degree lower than what we've got, than what we're getting coming out of the relief valve. Of course, there could be a tempering valve in there. I don't actually know what the temperature is inside the tank, but there you go. The thermal is showing 52.5, so that's, yeah, I'm going to put that within the margin of error there. If you leave it on for a while, then the gas igniter should kick in, and it should start heating up the tank again. Right, so I've still got that running in there, and I can hear it flaming away. That inlet gas valve there is like 38 degrees, and the cold water, yeah, the coldest is 20 degrees. So we've got 20 degrees coming in, and we can actually measure that here on the tap as well. I did measure that the other day, and I'm not sure if you can see that, probably not, but it's 247 degrees, because that's obviously the flame lighting this thing. So yeah, what the actual internal temperature is in here, I don't know. So all we can get is the outlet, you know, the relief valve here, but that could be coming through a tempering valve to prevent it getting too hot. I'm sure that's the case actually, and there's no direct temperature reading on the dial. So yeah, this is the outlet, and yeah, that's at 51. Hardly dropping anything, but you can see because the water's flowing now, the pipes are hot. Yeah, there's no loss in those pipes. Of course, it's a nice warm sunny day here, so the roof is probably pretty hot. So yeah, we're still in spring here. I've got 20 degree water going in because the pipe comes in from underground, so that's, you know, that's not surprising. And then we've got 51, 52 degrees going out, and we get all of that at the tap, so that's not too shabby. So yeah, we'll find out what the new heat pump system's like, but obviously, like, it's got to run hotter than 50 degrees internally to prevent, you know, bacteria and Legionella and all that sort of stuff. I guess you set the outlet temperature. I don't know. Maybe I can ask the guy tomorrow who's installing. He might know. Actually, ask Reclaim. What's the actual deal? You know, is it actually hotter internally, but does it have some sort of like tempering valve in it? Anyway, that is the before, and we'll now cut to the after. And here it is, magically installed by the Oompa Loompas. The heat pump is actually much bigger than I thought it would be. I thought it'd be a reasonable size, but you can see it compared to our aircon. Well, I don't know if I can get a decent measure on that, but if you can see it compared to our aircon, oh yeah, okay, it's a similar size to our a smaller aircon unit. This is a Mitsubishi Jobby, as is this unit here. This is actually Mitsubishi. It's of course got Reclaim Energy's badge, but I've been told it's been manufactured by Mitsubishi, and here we go. It's the model, that could be a Reclaim model number, made in Japan. All the best stuff's made in Japan. And it does say 2.3 kilowatts, but I was measuring the consumption remotely today, or trying to. I think it's around about that 1 kilowatt mark, but I won't know until I actually get the power meter on. Now, they actually installed a extra a double power point here for the control, one for the controller and one for the heat pump. Now, you can see the scanning. I can actually see the flicker on this LED display. You're seeing it worse on the camera because of the shutter. Anyway, so I have to RTFM on that, but they have set it to come on like from 10 a.m. to 4 p.m. or whatever, so that we use the excess solar. I might tweak that time somewhat. But anyway, yeah, it's got a thermocouple input, which goes down to the, well, what they call a sensor well down here, basically, and that's got the thermocouple. And this is the 415 litre tank. As I said, it's the biggest one they make. It's absolutely massive. They mounted it on like a polycarb base, and yeah, it does obscure. It's so big it obscures a little bit of the pathway through the side gate here, but we rarely use it, so that's not a big deal. It's a stainless steel jobby, and it did come pre-banged up. Look at this. They did actually show me that when they got it off the truck. They didn't do it on the getting it off the truck. I believe that was like, it just came out of the box. They unwrapped it and there it was. So yeah, it's good enough for Australia. Yeah, this is not the actual tank. The tank is actually inside this tank, surrounded by insulation, of course, because this, like, I can't feel anything on this. This just feels ambient temperature to me, but it's actually filled already with 63 degree water. I think it's set at internally. You can't actually change that, but it's manufactured here in Australia by Metal Dynamics Proprietary Limited. See, it says 400 litres, but I believe it's actually 415. Anyway, we've got the standard relief valve here, so yeah, I can feel that's pretty warm. We'll get some water coming out, and I'll measure that. That should be 63. Let's follow the pipework here. So we've got our cold water coming in here. That comes from up the top here. That just goes to a tap here. And then the cold water goes around here through. We can actually switch it off. And then it goes, well, I'll tell you about this in a minute. But yeah, then it goes down into the bottom of the tank here. And then, so the bottom water in the bottom of the tank goes up into the heat pump, which is this bad boy here. And due to heat pump action, yeah, just look at any how a aircon works, and it's the same way, or a reverse cycle aircon. It's exactly the same thing. And you get your nice hot 60 degree water coming out of here, and that just goes into the top of the tank there. And then this one on the other side is the outlet. So this is just a storage tank. There's nothing else inside it. So it comes down here. So this is our hot water output, and this goes into what's called a temper valve. And these are required under Australian law and for just common sense, because you don't want 63 degrees C water coming out of your tap, because that will ruin your day. And yeah, you can, give yourself serious burns with 63 degree water very quickly. So temper valve, what that does is mixes the cold water coming in here with the hot water down to a preset temperature. You can actually, it's got a little plug on the end there, you can flip that over and we can actually adjust the temperature. I don't know what it's set to. Usually they're set to like 50 to 55 degrees, something like that, because you don't want it too low, because then you're using too much hot water to get the temperature that you want, but you don't want it too hot to burn you. So the old gas one, we were getting 50-degree water out. Anyway, that's a very cool device. It's completely mechanical. So yeah, it uses some sort of like diaphragm that changes with temperature. Not exactly sure how, but yeah, very cool. And then that just goes into the house. So that is it. That is a heat pump hot water system, and as I said, the old tank was 173 litres. This is 415. In a normal day, we won't use like much of this capacity at all. We'll probably use like 150 litres. So good thing about this is that I can whack the power meters on here easily, and we can find out the the controller's on all the time, so we'll have standby consumption of the controller, and we'll have standby consumption of the heat pump as well, so I can measure both of those. They did install an extra fuse. There it is. It's the one on top there, hot water. It's a 20 amp jobby just for that outlet there. And they decided to mount it up on the bracket just because it was too much hassle to move the tap and everything else. And also, if you get flood in here, you don't want it like actually sitting directly on the ground. You'd have it offset, of course. But yeah, now we can like put some stuff under there as well, so we can use that space if we need to. But there you go, that is very cool. And yes, lots of people have asked, yes, a tank outside is very common here in Australia. For a house, it's probably the most common thing. So yeah, no worries. Like the house that I grew up in, which is probably in the late 60s house, that actually had the tank in the roof, but I don't think anyone does that anymore. So we'll use it tonight as a normal night, and I'll measure the consumption tomorrow to see how much energy in kilowatt hours it takes to reheat the water that we actually used. Temperature of the water coming out of here, and yep, it is 61. And my first test out in the laundry again. Yeah, it's hot. Oh yeah, it's Ernie Bernie. They set it to 55 by the looks of it, which I think is what they said they would set it to, but yeah, that is 5 degrees, 4 degrees hotter than what we had it before. You'll use less hot water, of course, because you physically mix in more cold water with it to get your desired temperature for your shower or your sink or your whatnot. So yeah, it's probably good to have it a bit higher, but geez, I wouldn't want it any higher than that. That really is Ernie Bernie. And standby consumption of the controller here, about 0.9 watts. That's all right, no wuckers. That's 1.8 VA. And we'll see what the pump takes. I'll switch it on. Nah, didn't do anything. Nope, fan's not going. Nope, nothing. So it's drawn a couple of watts in standby. VA on that, oh yeah, pretty terrible. 40 VA, but as I said, yeah, power factor of 0.07. Yeah, that's what happens when these sorts of things, yeah, that's what you'd expect. It's terrible, Muriel. But yeah, I only pay for the watts, so 2.7, 3 watts, yeah. So let's run through the numbers of what I actually measured and compare it with what I thought I would get before I actually installed this thing, because this whiteboard might be familiar to many people, or at least the people who are subscribed to my second channel, EEVblog 2. I did this quite some time ago. This is the original whiteboard for it, where I actually went through my old gas hot water and how much energy it actually used in megajoules, and converted that to kilowatt hours, and what it was costing me, and all that sort of stuff. And I was able to get a kilowatt hour figure per day and cost per day, and all that sort of stuff. And I was able to then speculate what I would actually get when I installed this Reclaim 400 litre heat pump system. So did it work out? Well, not really. The claim, I was a little bit off, and we're going to find out why. Anyway, I've got tons of videos on my EEVblog 2 channel, so if you want to see this video is a dedicated one, I'll link it in down below and up here and all that sort of jazz, go watch it. But a quick recap is basically my existing gas hot water system here. I got 5 different bills here, and I was able to extract the megajoules, convert them to kilowatt hours over how many days that was actually done here, and I was able to convert that to a figure in kilowatt hours per day we can directly compare to an electric hot water system or a heat pump hot water water system, which is just an electric hot water system, but it's more efficient. So the reason that we can do this is because on your gas bill, typically, I don't know, it might be different in different countries, but here it tells us the figure in megajoules, and that's just energy. You can convert energy from one unit to another. So the equivalent megajoules here, you can actually convert to kilowatt hours. There are a couple of little factors in here which they'll have on the bill, which is like the pressure and the environmental factors and stuff like that. But those figures are fairly stable. So we can actually convert that to kilowatt hours, and that's what I've gone. It turns out that if I averaged it over an entire year, my gas system every day was taking the equivalent of 12.8 kilowatt hours per day in energy. Now, of course, we're not going to go into the difference between the embodied energy in a gas, to actually mine and produce the gas and transport it and all that versus what is required to manufacture the solar panels and all that embodied energy stuff, right? It's a really complicated equation. We're just simply comparing how much energy a gas system uses versus how much energy a heat pump system uses. And based on Reclaim's figures, they've got a figure of 3 kilowatt hours energy consumption for 315 litres delivered per day. And that's, for a typical usage for like a family of 4. Now, we actually use less water than that. 315 is a lot because our old tank was only 175 litres. And we kind of did run out of that occasionally, but like on a normal day, we'd get nowhere near to running out. So, I don't know, we might use 120 litres, I'd be guessing. And if you're playing along at home, that actually works out to the cost of almost $2 a day to supply and deliver the gas energy. So that's $722 a year, and that goes into the payback period and stuff like that. But not really worried about that in this video. We just want to have a look at how much energy is being consumed by our heat pump system and how it actually works. And they also claimed that the power draw is around 1 kilowatt. Remember the difference between power and energy? I've done a video on that. Kilowatt hours is energy. Kilowatt is the instantaneous power that it's actually using, and it's around about 1 kilowatt. Mine varied from about 950 watts up to about 1.15, something like that, depending on the day, where it was in the cycle and all that sort of jazz. But yeah, their 1 kilowatt figure, yeah, it's pretty much spot on. Now, the good thing about it only drawing 1 kilowatt is because the entire purpose we installed this heat pump hot water system is so that we could use our excess solar energy during the day instead of just exporting it to the grid and getting paid an absolute pittance for it. So we're effectively using this new 400 litre hot water tank as a thermal energy battery. That's essentially what it is. We're putting in that 3 kilowatt hours per day, for example, and we'll go into the figures on the next whiteboard, but we're basically storing that energy. So we've pretty much got like a 3 kilowatt hour battery there, but it's being used as thermal storage, which we use the energy mostly at night when we shower, and then it reheats during the day. And the Reclaim system comes with a timer on it that only works between 10 a.m. and 4 p.m. when the sun's shining. And pretty much, even on a really bad day in the middle of winter, we're easily going to have 1 kilowatt of excess power available for our nominal 8 kilowatt solar installation. So pretty much after we've installed it here, and remember, this is a real pricey system. This is probably one of the, if not the most expensive heat pump system you could get. So you can get ones like half this price or even less than that, but we went with the best quality made in Australia one. So what did I calculate? Well, based on their nominal 3 kilowatt hour claim for 315 litres, I knew we weren't using anywhere near 315 litres per day, even though we do have a family of 4. So I actually took the existing tank as a measure, 175 litres per day, and then you just work out the ratio there, and I calculated roughly we should only take 1.7 kilowatt hours per day. Well, as we'll see on the next whiteboard, no, I got a fair bit more. We used a fair bit more energy than that, but I think it does actually make sense that I really wasn't going to achieve that. If you're wondering, and you should be, what is the efficiency of a gas hot water tank system, not instantaneous, and we're always talking about tank hot water systems here. I've also done a second channel video on instantaneous electric hot water systems as well, and why I didn't choose that option. So I'll link that one in as well. Well, it turns out that a tank-based gas hot water system is around about 60 to 70%
efficient. Now, my one is really old, many decades old. It's got high efficiency written on it, okay? So I took that as the upper end. Now, in my state of New South Wales here in 2015, they brought in new regulations that said that all gas tank hot water systems have to be at least 69% efficient, I believe it is. So I'm going to say that my old one was probably 70% efficient. And how much energy did it use per day? Average over the year, 12.8 kilowatt hours per day. So if we calculate 70% of the efficiency of that, it's basically 9 kilowatt hours per day of heat energy being put into that gas tank. The rest is lost on, I don't know how the flame works, the flue and the whole, actually heating up that thing. But where we were actually putting, it seems, around about 9 kilowatt hours per day heat energy into the water. And you've got to remember, that's for a 170 litre tank, okay? My new Reclaim one is 400, well, nominal 400. I think it's about I put 415, but I think it's about 420 litres is its real capacity. So, yeah, for a much smaller tank, 9 kilowatt hours per day compared to 3 kilowatt hours per day, which Reclaim claim here. And well, it's no contest, just in terms of pure energy consumption, a heat pump hot water system, in fact, in particular, a CO2-based heat pump system, because the new CO2-based systems are a bit better than the old school refrigerants used. They now use CO2 as a refrigerant in the more modern heat pump systems, and they're more efficient. They have a greater coefficient of performance, or COP. But yeah, there's no contest. A heat pump hot water system wins hands down compared to a gas system in terms of energy consumption. So let's now magically look at the results that I got over 9 days. And here it is. I got data over 9 days. There were actually some days before that, but I wasn't measuring all the parameters, and then the power failed. I've done a second channel video on that where my power actually ironically went out. Anyway, that's a second channel video. Go watch it. So I've got data over 9 days, okay, for my new Reclaim 400 litre, nominal 400 litre CO2 heat pump hot water system. And we'll go into how it actually works in a minute in terms of the tank. But what I've got here is how much energy did it use per day, because I was putting an energy monitor on it every day, and I was able to measure, 2.66 kilowatt hours, 3, so like basically anywhere from 2.54 to 3.13, I think, seems to be the range of kilowatt hours energy per day. So it's basically an average of 2.83 kilowatt hours per day, and that's not far off that 3 kilowatt hour claim for 315 litres consumption that Reclaim make. So why are we getting near that, even though I can guarantee we're using nowhere near the 315 litres, let alone the 400 litre tank that we're actually got here? Well, it turns out that, well, they're marketing figures, right? Now, they did actually give me some data for a site that they have in Tasmania, which is right down the bottom end. It's the map of Tassie. Little Aussie joke there for my Aussie audience will get what I'm referring to there. Anyway, it's quite cold down in Tasmania. But as it turns out, the CO2 heat pump hot water systems do actually work better. They're actually more efficient, ironically, in a colder climate like that. That has to do with the high pressure used in the CO2 based heat pump systems and the differential between the ambient temperature and the output temperature. So yeah, it makes a difference. So obviously their figures are coming from a more optimal environment. But anyway, my figures will actually change. I expect this average figure to change. It'll have a seasonal component as well. But it's almost summer here. It's a couple of weeks away from summer when I got this data, and well, 2.83 kilowatt hours per day. It's more than I was hoping for, but still not too shabby. And we've easily got like 3 kilowatt hours per day excess energy that we're just exporting to the grid, getting paid a pittance for, as I said, and we're now actually storing that. So I've effectively got, let's just say, a nominal 3 kilowatt hour thermal battery system. Beauty. So once again, right off the bat, it's under 3 kilowatt hours per day, or more than 3 times better than the equivalent 9 kilowatt hours per day for gas. That was actually the heat energy going into heating up the gas hot water system. It's 3 times better on a pure energy basis for heating up the water, let alone the losses, because this figure already includes the losses. So what other data did I get? Well, I got the maximum ambient temperature for that day. I didn't log that myself. I just took that from the Weather Bureau, but that was the peak temperature in our location during the day. Then I got the minimum ambient temperature as well. That's the overnight temperature. And then I got the temperature in the bottom of the tank. We'll go into the exact location of that in a second. And then I got the temperature in the top of the tank, which is actually the relief valve temperature. So I could actually measure that directly. This one came from the thermocouple inside the reclaim unit. I can hit a button on there and get the bottom temperature. So basically, this bottom temperature of the tank was the starting temperature at 10 a.m. when it switched on, that it, it had to heat up from that to 63 degrees C. So what I've done is I've tried to calculate the COP, or coefficient of performance, of this system, even though we can't really do that because we don't have enough. Even though I've got all this data, we still can't really do it. And let me explain why. But I'm trying to get a figure. Anyway, the coefficient of performance is the amount of heat energy you get out. Remember, this is heat energy you get out of the system. In this case, basically what comes out of the heat pump here, the 63 degree water here, what the energy that comes out of that divided by the electrical energy you put in to power this 2.83 kilowatt hours per day to actually get that amount of heat energy out. So it's just a simple ratio, this COP. And Reclaim actually claim a coefficient of performance up to like 5 times. And that's, the sort of like extreme end for a heat pump system, but this is a top quality one. It's the new high efficiency CO2 based refrigerant in there. And it gets maximum, it's pretty much one of the best ones you can get on the market. So I don't think we're quite seeing those figures, but as I said, don't have exact figure. It'll depend on environmental factors, incoming water temperature, ambient temperature, the amount of, how you cycle the tank and all sorts of stuff. So what I've done is also calculate the amount of heat energy required to heat up the water, in this particular case from the bottom starting temperature, and I've got to go into the details where this is a bit warm and fuzzy, but it's the best I can do with the data we've got available, as I'll explain in a minute. So Q here is the amount of energy required to heat up a body of hot water. And then because we're talking about water, we need the specific heat of water, which is around 4190 joules, and then multiplied by M, which is the mass of the water. So in this particular case, right, we've got a 400 litre tank. It's actually 420 litres, so they just round it down for marketing purposes, but actually 420 litres actual volume. But here's the interesting thing. The temperature sensor where they're getting this bottom temperature from is at about the 30% mark on the tank. And I've verified all this with Reclaim, by the way. They've actually sent me data on this. This is where I got it from. So I'm going to subtract the bottom 30% of the tank there and just assume that volume's not being heated up. I know this is all, a little bit how you're doing, but, we're just having fun here and trying to calculate a rough COP here, a coefficient of performance. So that gives us a volume of 294 litres. So if I whack that in there, 294 litres, then we have to multiply that by the temperature differential, which is the temperature you want to raise the water to. In this particular case, even though it comes out at 63 degrees Celsius, it actually heats it up until it reaches a bottom temperature here of 58 degrees Celsius. So we're going to run with 58 minus the bottom temperature, which is this one here, the starting temperature, and that gives us our figure, our kilowatt hour figure in heat. It actually gives us in joules, but then I've converted it over to kilowatt hours there. And that's the amount of heat energy required in kilowatt hours to heat up this volume of water from this temperature to that 58 degrees set temperature there. And this is effectively the amount of energy you would require if you didn't have a heat pump system and you had just the old school electric element, hot water, a direct heating electric element hot water system. You'd be using this much energy, but we're only using 2.83 kilowatt hours per day instead of 10, 11, 12 kilowatt hours per day that would normally be required because we've got a heat pump. The coefficient of performance, as you can see, just pops out here. It's anywhere from 3.7 to 4. 2.45, something like that. It sounds reasonable, but unfortunately, you can't really measure the true coefficient of performance on systems like this unless you actually know you actually have flow meters on the inputs and outputs to measure the actual volume of the water flow and the actual direct temperatures and stuff like that. So yeah, we don't really have that, but the numbers kind of sort of pop out, and Reclaim's figure, 4 is pretty typical, might vary between 4, 4.5, something like that. So yeah, it's in the ballpark. I like it. Now, one of the problems here is that the tank is not just at one uniform temperature inside. Unfortunately, there can be quite a substantial temperature difference in here. As I said, the temperature sensor, the only temperature sensor, is down the bottom here like this, and at the 30% mark, and it raises it until it keeps pumping the heat in until it reaches a set point of 58 degrees Celsius. And when you do that, the top of the tank is actually going to be at 63 degrees Celsius, because the heat pump actually pumps out a fixed 63 degrees Celsius water. So we've got what's called a stratified tank here, which means there's going to be a thermal gradient in here and thermoclines in here where there is actually differences in, of course, hot water rises. So there's going to be thermal differences in these layers here. So they've got that temperature sensor at the 30 degree mark. So that's where their set point is for actually stopping the heat going in like this. And by the way, yeah, it does run for about for that 2.83 kilowatt hours per day at around about that 1 kilowatt power draw. It does actually run for around about 3 hours, something like that. And I don't expect that to change much during the season. So you can easily have a timer on here to come on to just power this thing once per day. Now, of course, you have to keep the temperature elevated, and there's a reason that they have the 63 degrees coming out. That's to prevent Legionella build up in the tank. So it's also got a cycle that if it doesn't reach that temperature once per day, it'll pump energy in to ensure it gets there at least once per day, so it kills any Legionella and other bacteria stuff in there. So yeah, unfortunately, to get a true measure of the coefficient of performance here, we really need flow meters on here. So yeah, basically the cold water actually from the tap actually comes in here like this and goes out the bottom as well, and that goes into the CO2 heat pump, which then using the heat pump action transfers it from the ambient air. So the ambient air temperature is going to make a difference, as does the cold water incoming temperature like this, but it'll always pump out 63 degrees Celsius water like that, and then that slowly makes its way down via stratification in the tank until this temperature sensor reaches that set point of 58 degrees. And then during the night when you shower, it's just basically being pumped out of the top here, and that thermal layer, sort of stratification layers just sort of like go up as the extra cold water, because remember this is our mains pressure fed, so there's cold water kind of like being fed into the bottom, and there's hot water coming out the top, so those the stratification layers like move up like that, and how they mix and all that sort of stuff, I don't know, but there are thermal layers in there. And I did actually capture one day where the heat pump did actually turn on. This was actually the first day we used it. And you can see here that there was a 3-hour window there where it actually switched on. And then it was, anywhere from 950 watts to like 1.1 kilowatts, something like that. Pumped it in for about 3 hours. That 2.83 kilowatt hours on average to 3 kilowatt hours, something like that. That was enough energy to heat a 420 litre tank. Now here's an interesting graph of a CO2-based refrigerant hot water, heat pump hot water system like we've got here versus an old school refrigerant, the R410A refrigerant, which is a fairly typical one used. And you can see the coefficient of performance is higher over over the temperature range compared to that older refrigerant. Of course, the higher the coefficient of performance, the greater efficiency you're going to have. And you can see it's kind of like reasonably flattish down to like 5 or 10 degrees, something like that. So it's not too bad. So that's why in a colder climate, this is an output referred figure coefficient of performance. So that's why in a colder climate like Tasmania, you're actually going to be more efficient and you're going to do better than in a environment like this. But there is a semi-complex trade-off with the incoming water temperature and the ambient air temperature and the pressure of the refrigerant used and the thermal insulation of the tank and the size of the tank and the amount of, water flow that you're using, all that sort of stuff. You really can't measure these things, unfortunately, unless you have proper water flow meters and proper temperature sensors in there. But I've done the best we can, so it's not too bad. I rather like it. So there you have it. I hope you found that as interesting as I did. I love getting data like this and analysing the results. And, well, am I initially happy with my heat pump hot water system? Yeah, I am, even though I expected a bit less power consumption based on the amount of water that we actually use. It looks like it doesn't really make a huge amount of difference. And if you go in and analyse like individual numbers like this, there's kind of like not, it's hard to correlate anything because we don't know the exact amount of water that we actually used, and it's just difficult. All we can do is like, ballpark stuff kind of thing. Even though we've got like exact measurements for some things, it just is going to vary quite a bit with like the amount of water that we used. And I'm sure you think that you have the same amount of showers every day, but you probably don't. And there's a couple of baths thrown in there as well, I believe. So I do have those noted in my data somewhere, but I couldn't really find any correlation there. So it looks like we deliberately went for the bigger tank, and it looks like, it's a good thing because we'll now have much greater heat capacity, a greater thermal heat sink effectively for really not much, if anything, more in energy. So yeah, I'm quite happy with it. We're using our excess solar energy, around 3 kilowatt hours per day. As I said, that'll be seasonal, but we've got more than enough excess energy. Sometimes we're, like double digits, we're just throwing away exporting to the grid per day. We're not using it. So so this is step number one in sort of like storing that energy locally and using it. And we've gotten rid of our gas hot water system, which was incredibly old, even though it was a high efficiency one. It's nowhere near as efficient just in terms of pure energy consumption to heat up water compared to a heat pump. So just from a cost point of view, if you're willing to pay the extra money, it looks like this thing will probably pay itself off over 5 years, something like that, and then it's basically free hot water after that. And for those who are concerned about heat pumps are so noisy. Nope, it's about 36 dB, I think, is its rating, and even if you stand right in front of it, you can barely hear it going full ball. So yeah, noise isn't a problem at all. It is for those like larger pool pump, heat pump hot water systems. And in terms of reliability, I don't expect this to be any less reliable than any typical reverse cycle aircon we've got. We've got 4 reverse cycle aircon systems. One of them's 18 years old, hasn't failed yet. So yeah, and some others are like 10 years old, they haven't failed yet. So I don't expect this one. It's a quality Japanese Mitsubishi, I believe it's made by Mitsubishi, quality pump. So yeah, I don't I think, it's not going to die in the first 5 years. Before it pays itself back. I'd be very surprised. So I'm liking these heat pump hot water systems so far. Uses excess solar energy. It's a good choice, and certainly a good choice if you've got an electric element, a direct heating element electric hot water system, as you saw before. Yeah, I didn't actually erase it. There you go. What was it? It required like the equivalent energy. No, I did actually have it on here. It required the equivalent energy of like 10 to 12 kilowatt hours per day or something to heat up that volume of water, those temperature differences and stuff. So, it is significant advantage. As I said, like coefficient of performance is actually, you can achieve well over a coefficient of performance of 4 times. And no, this is not over unity. It's heat pump systems, okay? This is not breaking the laws of physics, Captain. Even though we're only putting in 2.83 kilowatt hours per day of electrical energy, and we're getting out, the equivalent of 10 to 12 kilowatt hours in heat energy, that is a different thing to the electrical energy used. And of course, for those who are saying, oh, 5 years something payback, that's too long. Well, we could have paid half the price of this system at least. In fact, in some states, I believe you can almost get them for almost free installed. They're with government rebates and stuff like that. They're real low quality, you know, made in China crap systems. But the company that I use that installed those, they said they refused to even install those real crappy bottom of the line systems. They just break down. It's not worth it. So yeah, you could save some money up front. So we paid the extra for like a top of the line, made in Australia system, Japanese pump, and it should last quite a long time, I hope. Anyway, I don't know, I'll come back in a decade, 5 years, I might give you a payback period thing. And of course, with the rising gas prices here in Australia, and it's happening everywhere, yeah, the payback could even be shorter than that. So there you go, heat pump hot water system. I'll keep you updated. Any extra videos I do, they'll be over on the EEVblog 2 channel. So I hope you liked that and found it useful. If you did, please give it a big thumbs up. Remember to subscribe, hit the, subscribe thing, the bell icon and everything, just in case YouTube's stupid algorithm unsubscribes you or something. And that's the way to get notified, and also exclusive videos over on my Odyssey channel as well. And leave your thoughts and comments down below. And also on the EEVblog forum link down below. Catch you next time. Oh yeah, if you want one of these 555 timer t-shirts, I'll leave the link down below. It's part of the merch.